Question. The CP for what, sorry?
The individual CP.
Yeah, if it's in a problem, I'm definitely going to give it to you or tell you, look it up in this table. The problem is once we start doing propulsion systems, the temperature is going to vary, and the CP is going to vary according to the temperature. So what we're going to have to do, we're going to have to use some tabulated CP values to modify this for some functions for CP. But for a problem, if I give you a problem, I'm most likely going to give you that value and tell you, given this table, for example, this temperature, look it up and try to get the effect of it. But yes, it's given. So these are not CPs, heater formations, things like that. That is expected that it's going to be provided in some form. You're not going to get it out of here. The only thing is the number of molecules, especially for fuel. That's the important thing. And air too. Concentration levels for air. That should be well known by now. 0.79 and 0.21. These are expected values. So these are things I'm not expected to give you. Because we already know air is not going to change. And this is something that we have to do. To actually have combustion or propulsion systems, you're going to have a hydrocarbon and a air mixture in general. But do we have any questions on this?
Yeah. So looking at the equation, so when you run either rich or lean,
Yeah.
I mean that you're always going to get a lower adiabatic flame temperature, right? Like so the equation condition will always be the highest temperature possible.
Yes.
That's right.
Yes, a very good point. So your colleagues pointed out that if you run rich or lean, that's going to actually affect your heat of combustion, and therefore your adiabatic flame temperature is never going to be higher than the stoichiometric condition. And yes, that stoichiometric condition is you're ideally burning every drop of fuel you're putting in with the right amount of oxygen you're putting in there, and therefore you're going to get the highest adiabatic flame temperature for that fuel. So it's a good question. Any further questions? We're good? We close this section? Okay. All right.
No,
so with
speak.
that, we'll be done with chapter 2.
Ooh.
Yeah, exactly. And we're going to begin to do high-speed aero review, compressible flow review. So I'm relying on you telling me how much you know and how much I'm reviewing that might be redundant that I can do faster. So let me know as I keep going through it. I'm going to assume that you don't know anything.
No, now you know.
And we're going to go over the equations from the beginning, and you tell me what you're talking about. We already know very well, or I'm familiar with this.
Got that on video, but
moving on, and that will help us get into propulsion systems. Right now, we magically have to review a semester. I mean, think of this. Everything that we're doing so far is reviewing your fluids, your thermodynamics, and your high-speed aero. So I'm lumping in energy transfer. It's like we're lumping in all these courses into a very small section of the semester. So there's a lot of material to cover. But I mean, propulsion systems is rocket science, right? So, and, you know, take pride in the fact that you are rocket scientists. So, there you go.
Okay.
So you have to know all these in order to be able to apply these to the systems. So that's why it's very, very complicated in a sense. But we'll get to the fun part. Once you review all this, it becomes, as said, very second to nature to you, because you have to use it all the time. The problem starts to become the components complexity, how you're treating the engine, how many busters you're gonna have, and what Mach numbers, altitudes, and pressure effects you have to deal with. So let's briefly begin compressible flow, and we'll stop at some point. So this is chapter 3 in the book. I recommend read from 3.1 to 3.6. So we make a consistent assumption when we're dealing with compressible flows in the engine, which we assume, as I said, steady flow. However, experiencing
Not all the time.
density changes. This is why it's called compressible flow, because you are getting a compressibility effect. You're compressing that gas and the density is changing. The other thing is this class is mostly in the steady state 1D assumption for compressible flow. So let's take a look at the general conservation equations. Or conservation law. So if I assume I have some CD nozzle, we're not going to do CD nozzles right now, but I want to drive the equations using it, at least for a converging section of the nozzle. I have some velocity, and I have some area, and I have some density, and I have some dx that things are actually getting compressed across. This is some x-coordinate system, and on the other side, I'm going to get u plus du dx multiplied by dx, a plus the rate of change of my area over that distance multiplied by dx, and rho plus d rho over dx multiplied by dx. Just the control volume approach, meaning that whatever I'm putting in is equal to what goes out plus the rate of change of what happened during that displacement. So if I apply my mass conservation, which we've been applying so far, the rate of change of mass in my control volume over time plus the integral, Brown's transfer theorem, rho u that multiplied by the normal component ds equals to 0. So if I expand this, what we'll get is rho plus d rho dx times dx. So this is 0, obviously steady state equals to 0. Multiplied by u plus du dx multiplied by dx multiplied by a plus dA over dx multiplied by dx minus the import, which was in this case rho a u is equal to 0.
Who's that? Who's that?
So let's assume that dx was small, so take the limit of, we're saying dx is almost going to 0, neglect. So from there, what do we end up getting? We end up getting partial rho u a over dx is equal to 0, or what we're used to as dA over A plus du over du plus d rho over rho is equal to 0. You've seen this equation before, right? Saw it before? Must have seen it before.
Yeah.
Okay, but so this is equation 3.1 in the book. So we'll stop here and do the same conservation of momentum next class. But this is the compressible form of the conservation mass.
Order of graduation down.
Oh shit, that's today's last day, right?
Today's last day.
Shit. Okay, well. Say bye, guys.
Later, YouTube. Say bye to everyone in the back. Later, YouTube.